Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. This is part 6 of the 13-part video series of General Organic Chemistry. In the last one, we saw electromeric and inductomeric effect. In this one, we're going to introduce you to the concept of intermediates and transition states. At the outset, let me give you a brief idea about what it means. You see, when a reaction happens, when two molecules approach each other, they hit each other in an appropriate manner to form the product. There is a complete process involved in this. Now, it may just happen that two molecules come and collide, and something goes from one of them, something joins from the other one. Just like if you remember the inductomeric effect that we saw, the OH minus approached from the back side and the Cl went away and the OH went and joined with the carbon. So that happens in one single step. But it's also possible that some reactions may happen in multiple steps. Now, what happens when a reaction happens in multiple steps? What happens is that the reactants may collide with each other, or maybe one reactant may break into some species, which further reacts in the further step. But these species are never found in the overall reaction. When you write the overall reaction, you only write the reactants that you started with and the products that you finally got. What species you got in between this entire process is something which is never revealed in the overall reaction. For that, you need to know the reaction mechanism. So those species which are formed in some step but are consumed in the subsequent steps, these are called intermediate. So let's have a look at that. So in the beginning of a reaction, there are reactants, and at the end of the reaction, there are products. Okay, we are clear on this. If a reaction takes place in one step, then reactants directly convert to products. We are okay with that? But if a reaction takes place in more than one step, then there would be some species would form in some steps and would then be consumed in the subsequent steps. These are called intermediates. Now, intermediates are real. Their structure, hybridization, shape, etc. can be known with a great deal of accuracy. Their presence can be detected by several experimental techniques like spectroscopy. The bonds present in an intermediate are complete bonds, and charges present are complete charges. So if there is a bond in an intermediate, it is either there or it is not there. And if there is a charge in an intermediate, it is either there or not there. Of course, all the effects will work. Inductive effect will work, resonance effect will work, but barring these effects, whatever these effects make a bond to do, because these effects will also, for example, resonance effect, will make a bond partial. But if we ignore resonance effect, let's for example assume that there is no resonance effect happening, then you will always find the bonds are complete. When you draw the Lewis structure, you will draw complete bonds. You will not draw partial bonds. And when there are charges present, they will be complete charges and not partial charges. An intermediate can show inductive, resonance and hyperconjugation effect. And the lifetime of an intermediate is longer than a single molecular vibration, which is the reason why we are able to measure this. You don't have to really go into details of this, but just imagine that a single molecular vibration is perhaps the smallest event or the fastest event that can be studied experimentally. And anything that happens slower than that can also be studied experimentally, but anything happening faster than that is difficult to study. Now, for a chemical reaction or process, an energy profile or reaction coordinate diagram is a theoretical representation of a single energetic pathway along the reaction coordinate as the reactants are transformed into products. Reaction coordinate diagrams are derived from the corresponding potential energy surface or PES, which are used in computational chemistry to model chemical reactions by relating the energy of a molecule to its structure. Now, this is something which is an amazing piece of theoretical work that actually works. You see, most of the time, what happens is that we as scientists would first look at the experimental behavior of a molecule and then give an explanation. The entire science is about that. Science is about explaining facts. Science is about explaining what is observed. Now, in doing so, it will develop some theories. To test the theory, sometimes it will tend to predict something before the experiment is done. And if the experiment works in consonance with what is predicted, we say great. Or if there is some kind of a deviation, we'll try to figure out why is the deviation. And then we might even change the theory, which is how science progresses. Now here is a new branch where we predict something without anything. And with that, we are able to figure out what actually happens in a molecule. So what is a reaction coordinate diagram, or a reaction coordinate, or you can even call it the progress of reaction, stuff like that. Basically, an energy profile diagram is a diagram between the progress of reaction versus its energy. Now, what energy are we talking about? It could be free energy, it could be total internal energy, it could be any kind of energy, and different energies will have different types of diagram for a reaction. So, if you're talking about the total energy of a system, just imagine if we were able to look at the reaction, and at every moment the reaction is taking place, we're able to record its energy, and then we plot the progress of reaction with its energy. Wouldn't that be great to understand a reaction? This is exactly what is done in theoretical chemistry. This is not done experimentally, because experimentally you can never calculate the energy of the entire system while a reaction is going on. You can't do that. You don't have a camera looking into a reaction that also records how the reaction is happening, that is able to see all the molecules, also record its energy in the process. No, that's not the way it works. This is done theoretically. We do mathematical modeling. We look at how a reactant looks like. We look at how the two reactants look like. And then we figure out what the product looks like. And then we give an idea as to what might have happened when these two reactants approached each other. Based on that diagram, the energies are calculated. At each and every instant, the energy is calculated as the two molecules are approaching, and they are plotted together with the progress of reaction, or maybe the time axis. This is called a reaction coordinate diagram. The reaction coordinate is a curve that follows the pathway of a reaction and indicates the progress of the reaction. For a single step reaction, the energy profile diagram could be as follows. So, energy y-axis, x-axis shows progress of reaction. Now let's look at this. Let's assume the reactant is somewhere here, and then the product is formed. Every reaction follows a pathway similar to this. Perhaps not as smooth, because we can never experimentally verify. We can only model it and try to match some of our theoretical predictions with the experimental results to give a better idea. So this is how a single step may look like. Now let's look at a two-step reaction. Now the energy profile for a two-step reaction could be like this. Remember, I'm saying could be because we really don't have any reaction to work with right now, and there's no way to tell where the reactant is and where the product is. So let's assume reactant goes here, and you can see two mountains. This is reactant and this is product. Now this fellow, can you see, is the product of the first reaction and the reactant of the second reaction. So the overall reaction, you will find the reactant in the product. But this guy is formed in one step, is consumed in the next step. This fellow is intermediate. Now I just want you to read this paragraph first. Take your time, pause the video after the paragraph is completely shown, read it for a while and try and understand what it says. Now in the Harry Potter series, Remus Lupin changed to his werewolf form when the moon was full. But he didn't go from human to werewolf just by snapping his fingers. The fangs and the hair had to grow, the spine curled, the hands became more paw-like, and the fingernails lengthened into claws. If you see the movies, the business of transforming from human to werewolf didn't look like a whole lot of fun. You can imagine that the extent to which Remus disliked transforming into a werewolf was proportional to the pain involved. That point of maximum pain, maximum energy, where Lupin is half human and half werewolf, is a lot like a transition state, and this is known as transition state. So what I basically am trying to tell you is, in this step, which is the part which has maximum energy, this is called transition state. In this part, which is the state which has maximum energy, it is this transition state. Transition state for first step, transition states for second step. Now, like the most painful part of transforming from human to werewolf, a transition state is a local energy maximum. It has partial bonds and cannot be isolated as an individual molecule. Contrary to many claims, transition states are real species. In each step, a real state can be imagined between the reactant and that step and the product of that step. Transition states may resemble the reactant or product more than the other. It all depends upon to whose energy the transition state's energy is closest to, and the structure of the transition state, however, is imaginary or an estimation. Its presence can never be proved. Now, let me make this clear to you. The lifetime of a transition state, the highest energy point, because of being the highest energy point, the lifetime of the transition state is the lowest of all the species during the progress of the reaction. And this is actually lower than a single molecular vibration, which is why we are not able to ever understand what a transition state looks like. There is no spectroscopic evidence that it is formed. And since we don't even have the proof that it exists, there's no question of understanding its hybridization or shape or whatever. All of that is pure imagination. But these imaginations actually help a lot, and that will go for later on. But you need to understand transition state. Transition state is real because the very act that we know that intermediate is formed, or we know the product is formed, we know the reactant is there, and we know that just by snapping its fingers, the reactant cannot become a product. It has to undergo through a series of steps. And in these steps, there will be some orientation of the two reactants. So transient states are real. There has to be some situation where the energy reaches the maximum. And there must be some kind of an orientation between the two reactants. We can never see it. So we can never say transient states are imaginary. They're not. They must be real. But the fact of the matter is, it is not difficult to. It is so difficult to study transient states. We can never prove its existence. We can never study its hybridization, shape, structure, nothing. Every step of a reaction has a transition state. If there are n steps in a reaction, then there would be n transition states and n-1 intermediate. So here I'm going to give you an example. Let us take the SN1 reaction of R3CCl with OH-. Now don't bother right now about what is SN1 reaction, etc. You just have to understand this reaction the way it is happening. So here you will notice R3CCl plus OH-, the overall reaction looks like this. Basically what is happening is this OH fellow is replacing the Cl. So this is the reactant R3CCl, and as you can see there is a tetrahedral geometry of the 3R with Cl, and this is the product, of course. And as you notice, this COH bond is bent because it's not linear. I could have drawn the H here, it's not true, it won't be linear. So I've drawn the H here, so it's a little bit bent, but the carbon still holds the tetrahedral geometry. This is the product, okay? So this is the reactant and this is the product. Now let's see how the reaction happened. The reaction actually occurs in two steps. In step 1, the R3CCl breaks into R3C plus and Cl minus. And if you notice, R3C plus was never seen in the overall reaction. We just saw R3CCl, we saw OH minus, we saw R3COH, we saw Cl minus, we never saw this. And this is an intermediate. It is formed in one step and then consumed in the other. So let's look at this. How does this reaction happen? R3CCl is there, and then it breaks, and you get R3C plus and Cl minus. And as you have a look at this, have a look at this again. As you look at it, remember the 3 R's, they are also moving, even though this is the bond which is breaking, but they are moving because the R3C plus is planar. So as it is moving, the R's are also moving to get a planar kind of a shape. Now imagine if I were to stop this at the highest energy point. If I had the power to do that. This is the reactant, okay? As it is breaking, if I were to randomly stop it, because I really don't know where the transition state is, let me stop it here. This is transition state. I really don't know where the 3 R's are. I'm just guessing. And then if I let it go further, it shows you the intermediate. Now let's go for the second step. Remember, the second step is going to consume the intermediate. So R3C plus now attaches with OH minus to form R3COH. So this is the carbocation, intermediate. This is one of the reactants, OH minus. Look what happens when they approach each other. The 3 R's are moving back, the H is moving down to give the bent shape, and the carbon the tetrahedral shape. Have a look at it again. It was like this. As they come closer, the 3 R's move back, the H moves down, and the carbon gets tetrahedral, the COH become bent, and this is the product. Now imagine if this were to happen and I were to stop it somewhere in the middle, I don't know where, not exactly in the middle, but somewhere in between the two situations. Let me stop here. This is transition state. I really don't know what it looks like. I'm just guessing. And then if I let it go further, it becomes a product. So that is the end of this video, video number 6. This is the introduction to intermediates and transition state. I hope this video was helpful to you. If you need to watch it again and again, watch it as many times as you want, go ahead and do it. With that, this is Kalyan Kumar from Chemistry Universe signing off. Have a wonderful day. Goodbye and thank you for watching this.